Okay, so covering chapter 6 on telescopes. We're looking at a image of the James Webb Space Telescope to start things off. And we'll get to some more details about that famous telescope, but we're going to cover some basics first. And these are going to kind of start with some older fashioned telescopes to some degree. And that's gonna, we'll kind of see what I mean by that. But what is a telescope? So it's a device used to observe astronomical objects. So it's going to be a, you know, a wide, I mean, this definition is meant to be wide ranging. It can capture a lot of things. And we see that with the next bullet point here, where we're told that a telescope gathers light and other types of electromagnetic radiation and brings them to a focus. So by a focus, it just means that there's going to be some sort of clarity to the image. So, you could focus on a planet, you could focus on a star, you could focus on a galaxy, and those different distances would require a different focus. Um, so when we say light and other types of electromagnetic radiation, that is directly referring to what we saw in chapter 5 when we talked about the electromagnetic spectrum. So light is really just short for visible light. And sometimes the term light, as I believe I mentioned before, can actually be used for all types of light, even the invisible types. Although you're less likely to refer to radio waves as light, you still kind of can when you talk about all types of light. But recall that another term, an encompassing term for everything on the electromagnetic spectrum, from the shortest wavelength gamma rays to the longest wavelength radio waves, was called electromagnetic radiation, with visible light being a very narrow band, somewhat in the middle of all those types of light. So when we talk about telescopes that look at all those types, because they are all investigated in one way or another. A key principle and purpose of a telescope is to observe objects that are faint. So the telescopes allow for the observation of fainter objects. Fainter than what? Fainter than you could see with the naked eye. So we are talking about being able to see things that just wouldn't show up when we looked at the sky. Even if we looked at the sky in a place where there was no city lights, no light pollution. So, the night sky was as dark as it could be, was as clear as it could be without any clouds or precipitation, fog, or anything like that. You look up in the sky, you can only see so much. But if you use a tool other than your eyes, you're able to see more. And why that is, well, maybe you already know, but we'll briefly mention it in just a minute. But, in other words, why you can see fainter objects. So, quick rundown on the history. The telescopes were invented in 1608 or thereabouts, not by Galileo. We saw in our timeline that the telescope was invented by a different, early inventor, not as well known as Galileo. And they were made famous, at least in the retrospective of history, by Galileo because of his use of them. But he did not invent them. He just, was exposed to them. They were being used, and they were, kind of just being created around the time of his life of his lifetime. Okay, so it points out that he heard of the invention. All right, he made his own, presumably after seeing one, or maybe just from a schematic. And then he was the first to at least publish, and the first that where we know of his observations to observe the sky and record them. So no one else had used the telescope in that way. That is remembered by history, right? They're most likely primarily being used as periscopes, so being looking at objects that are far away on ground, the same way that we would use a binocular today or a periscope, to see things that are far away, like for for shipping and things like that. And just imagine the pirate pulling out the periscope, right? So that's the same, almost interchangeable with an early telescope. They use the same types of lenses, the same principle. The only difference is you turn the telescope up to the sky. Okay, so what kind of are the types of telescopes? What are the key aspects of them that we want to know? All right, well, let's talk about three types of telescopes based on how where their focus is. So this is where they're concentrating the light. In each case, the light that comes in kind of comes in as straight because the source of the light is so far away. And one type of telescope is a prime focus, where there's no additional mirrors used. So this is and by the way, let me clarify that all three of these types of telescopes, with their varying focus, are reflective telescopes. This is not the type that was used by Galileo, who used a refracting telescope. Make sure that you are clear on the two types. A refracting telescope uses a lens to bend light. A reflecting telescope uses a mirror to bounce back or reflect light. But they both can achieve the same thing, which is a focusing. In the case of both of them, whether it's the lens or the mirror, a curvature is required. You can't focus light with a exactly flat piece of glass. You have to have a curved piece of glass to focus a light. Think of a magnifying glass and its ability to focus sunlight onto a single point when it's used to, say, start a fire. Well, that's because of the curvature of the lens in that magnifying glass. It's that same curvature is what allows letters to look bigger when you're using it to magnify the size of a newspaper or a book. Well, with a mirror, you'll have to have some sort of curvature as well. That curvature can be parabolic or circular, but it has to have some way to focus. We can see a slight curvature if we look at the prime focus, because it doesn't have to be large, but it is there. Okay, so this is not a plain flat piece of reflective material. Instead, it is a curved mirror. Um, if you think of a curved mirror, you might want to think of a fun house at a fair, for example, because those mirrors that make people look shorter and smaller use curvature to achieve those weird effects. So this is that type of mirror, but instead of just creating a distorted image, it's concentrating the light, it's focusing the light.
I'm
Okay,
sorry,
so
Mr. Trevor, excuse me, I apologize. The two
go ahead.
words, you said it was reflect and refract. Did I hear that right?
Yes, yeah. So reflect and refract.
Refract. And
Yep.
then
So
Galileo used the
refracting telescope.
refract. Okay.
Yep. So, I'm just going to write it real fast. So, and that's actually what we see. I just went back a slide, so you notice that that's what these type of telescopes are. The long ones are refract. So this is a refracting telescope. This would be the adjective to describe it, refracting. And then this one here, all of these ones are reflecting telescopes. All right. So quickly, because these details are, although you're responsible for them, won't always come up, are a Cassegrain focus and a Newtonian focus. These are really kind of what modern reflecting telescopes are based off of, and they all include a more than one mirror. So in the case of the prime focus, there's just that one curved mirror. When you have a Cassegrain focus, now there's a hole in the back of the main or the primary mirror, that's the term, and that allows the light to reflect off the secondary mirror, which you can see kind of placed in the middle of the shaft of the telescope. And so ultimately, the focused image is being created directly behind the prime mirror. You could then imagine an eyepiece placed at that location. All right. And none of these are showing the eyepiece, which would be that, what you actually look through when you see the image. Obviously, the really basic one, it would be difficult to kind of get the eyepiece placed, which is why they were kind of outdated. But then we get to a Newtonian focus, which is a instead of having a hole in the primary mirror, the light is redirected with an angled mirror. So here we have light bouncing off that curved surface and then bouncing off a planar surface, so reflecting off a flat mirror being like the kind that you would, look through in your bathroom, just actually, flat, a plane, not curved. And so why would we use a not curved mirror? Because we're just redirecting the light. We're just bending it. Maybe it's not the great best term because I would use that term for refraction, but just causing it to be, angled up. In this case, basically straight above, so we can view the image above the shaft of the telescope. So we can look at the light coming out of the side of the telescope. All right. So this slide is called Powers of a Telescope. We could kind of think of this as the purpose of the telescope, but it also, that word power, it has a direct meaning because it actually comes up in the definitions or the key terms that are that we're referring to down below with each of the bullet points. So we've got light gathering power, resolving power, and magnification power. And what each of these refer to is some different aspect of what a telescope does. So let's talk about the first one, which arguably is the most important, although often not the first one that people think of that are not astronomers, or builders of telescopes. And that's light gathering power. All right. So this ability of telescopes, first of all, depends on the square of the size of the primary lens or mirror, and larger is better. So what this means is how much light you are focusing on that single point. So with a bigger mirror, no matter what type of mirror you're using, all right, or lens. So because in both cases you're concentrating the light onto a single point. If you have a bigger lens or a bigger mirror, you can concentrate more light onto a single point. And that means that you're making fainter objects brighter. So when we talk about light gathering power, we're talking about the ability of telescopes to make fainter objects brighter, to extend what we can see, to take something that we can't see with the naked eye and have something that we can see with a telescope. This idea of light gathering power is so important for telescopes because that's usually what they are designed to do, is to see faint objects. That's the the primary goal of telescopes, because the other aspects of optics are fairly limited when it comes to telescopes. And I'll try to explain that with the next two powers and kind of as best I can, kind of without trying, without giving you a whole course on optics, sort of tell you why that is. Okay, so the other two powers of a telescope are the resolving power and the magnifying power. All right, so let's quickly just define these. The resolving power depends on the size, so not the square of the size, okay, just the size. So we've got if I write a proportionality, I'm going to have power for the light gathering. So this is just going to be LG for light gathering. And this one is going to be proportional to the area. So that, area being in square meters, literally, you look at that mirror, it's a circle. So it'd be pi r squared, right? That's the area of a circle. But I'll just write area. Okay, the area of and be same for a circular lens, squared. But then when we talk about resolving power, I'll finish defining in just a second. So this would be R. So R, yeah, just R for resolving. And then proportional again. Okay. Oh, by the way, I'm sort of using a different proportionality symbol. So here I'll be more consistent. Sometimes that one's used, right? So it's almost exactly just half of the other one. But anyway, we'll use the one that we've been using. All right. So there we have it's proportional to area. So you got that difference, right? That being proportional to the square of something means big effect, right? You double the size, that really matters. But having a linear or direct proportionality, still, bigger is better, but not it doesn't give you as much, right? Your returns are not as dramatic. So depends on the size, getting back to resolving power of the primary lens or mirror. Okay. And a larger lens or mirror will have a smaller resolution, and a smaller resolution is a better resolution. Okay. So what resolution refers to is the smallest, usually angular distance between two objects that telescope can discern. So if you have a resolving power of 1 degree, the smallest thing you could see is 1 degree. Anything smaller, you wouldn't be able to make it out. And that often comes down to being able to discern between two separate like objects. So you've got two dots, and if those two dots are separated by if less than 1 degree, if that's your resolving power, then you wouldn't be able to tell. They would just look like a single dot. They're just, you wouldn't they'd be within each other's blur, so to speak, right? So it would just be one large blurry dot. But if you had a resolving power that say was a tenth of a 1 degree, well, that's plenty, right? Now you have that smaller, smaller resolving, smaller resolution. So now you can clearly tell that those two dots that are 1 degree apart are two separate dots rather than just one big blurry dot. Hopefully that makes sense. I could, continue to explain it for a while, but for the interest of time, I'll kind of leave it there with just one other reference to not telescopes, but the human eye and looking at small things, in hopes that this will have it make more sense to you. If you look at if you look at the smallest thing that you can, right? So if you want to, you know, investigate a piece of dust. Imagine you're doing some really like fine work on something, whether that's painting or like cleaning something, like you're trying to repair something that's really small, like a small piece of jewelry or whatever it is, right? You're really straining your eyes to see the smallest thing you possibly can. Well, then you got imagine you want to see like two separate pieces of it, right? Like two separate pieces of dust. So I guess just imagine you're staring at dust and you're trying to find the smallest pieces of dust you can, right? On a really well lit tabletop, and you're looking at those two pieces, a bunch of pieces of dust all spread around, and you notice two that are really close together, but you can tell that they're two separate specks. Okay. Well, like about how far apart those two specks would be for the, kind of the quote unquote healthy human eye, the human eye that has, 20/20 vision. Well, that distance would be 50 microns. That's the resolving power of the human eye. That's the smallest distance that we can see. And it's interesting that it's not an angle because that's based off of we can only focus on things that are so close. By the way, it's 25 centimeters. That's called the human near point. If something's closer than that to your eyes, it becomes blurry. Right. So if you have something at that near point of 25 centimeters, the distance between them is going to be 50 microns, which is 50 times 10 to the negative 6. Anything smaller, you cannot tell apart. The two specks would look like one. Okay. So finally, magnifying power. This depends not on the area of the lens at all, but on the focal lengths. So it actually depends on the length of the telescope. The other two didn't. They just wanted a big mirror or a big lens. This requirement would be a long telescope. So to get high magnifying power, you would need a long telescope, especially if it's a refracting telescope with a lens instead of a mirror. So this is going to be M for magnifying, the power of magnification. And this one is just proportional to L, where L is the length. And if I wanted to put these values of A and L into a figure, then this right here would be our A value. If I was to look at it from the side, it'd be the whole cross-sectional area. And then L would just be the whole length. Imagining that this is the end. Okay, make sure that's clear. And Well, talking about the focal length, um, it's going to be of the primary mirror. So longer focal length means higher magnifying power. And just like I've said a few times, light gathering is the most important. And now we got to the bottom and we got into the least important, which is magnifying. So that is a really wide, like a widely held misconception about telescopes. And I bring that up in no way to, disparage people and say, oh, they're so stupid. They don't know about telescopes. No, not at all. I don't imagine in any reason why people would know details about telescopes, unless, they're taking an astronomy class, or they teach it, or they build them, right? So, but anyway, so telescopes, they you think about them and you think that they might work like a microscope, because they have actually a lot of the same principles. And with a microscope, like you'd see in a laboratory, or a doctor's office, well, they're actually all about magnification. That's their primary purpose. And the most important power for a microscope is the magnifying power. And so they really optimize that magnification. You can get a magnification of, 300, 500,000 times, right? You can see things that you just wouldn't be able to see. So don't we want to do that with telescopes too? Don't we want to be able to make things bigger? Because shoot, when we look at images of, Saturn through a telescope, we can see its rings. Isn't that because we magnified it? Yes, we actually did, right? So sometimes magnification actually yields some interesting results. But okay, that's all within the solar system. That's obviously a small slice of astronomy. Once you get out to distant stars, even nearby stars, let alone, talking about things kind of outside of the galaxy, being able to magnify them doesn't really make much of a difference, because although it could, the it never will. Because the actual amount of a magnification that would make a difference, so that you could say see a star, through a telescope, and I could make it out as a circle and be able to see it like we see our own sun, with details, showing its sunspots, or able to look at a planet around another star and be able to magnify it so much so that you could see it's like continents, or what its surface looked like, be able to see its polar caps or something. That's never going to happen. It is there's just limits of light, just plain and simple. That means that magnification will never be achieved. So there's no sense in focusing on magnification if it's never going to yield good results. So astronomers basically have just given up on magnification and moved on to other ways to investigate the cosmos, other ways to analyze things. Okay. And it basically, what I'll say on that is, look back on chapter 5, and of the ways that all those different types of light were described, the ways that we talked about the Doppler effect, the way we talked about, how thermal radiation corresponds to temperature, because those principles don't require magnification. They just require identification of wavelength or frequency. So that's what astronomy is all about to a big extent. And actually magnifying would only matter for a few in solar system cases. Speaking of limitations of telescopes, okay, we've got things that we can't avoid. And I'm going to quickly run through these because they're not going to be crucial to the rest of our discussion. We've got chromatic aberration. This comes down to the fact that colors separate. I'll quickly tie this in with something that you saw back when we talked about lunar eclipses. Um, and that's when the moon goes behind the Earth and it turns red, right? And it turned red because of the reflected sunlight off the moon from Earth's sunsets, which then begged the question, why are those sunsets red? And we saw that it was because the red light made it to the atmosphere, because the red light bent differently than the other wavelengths of light? Well, that's the idea that leads to chromatic aberration. Different colors bend at different amounts. So when you take white light that comes from a star like our sun, which is composed of all the colors of the rainbow, well, then that light is going to separate. And this could apply to other types of light as well. Light that's primarily blue is still going to separate into different wavelengths because it wasn't most likely all blue to begin with. So unless your source of light is just like, not a continuous spectrum, unless your source is, say, a emission spectrum, which is just a few, particular bands of light, a few particular, defined colors, there will be separation. So for any continuous spectrum, you'll have some amount of chromatic aberration. Those different colors will bend differently, and that means they're not all going to focus at the same point, which is kind of the consequence of that bending. Aberration just means like, blurring, destroying the image. Limited size. Okay. So you notice that the size of the lens or the mirror was very important for both that resolution power or resolving power and the light gathering power, the primary uses of a telescope. Well, that means that you have to have these really big mirrors. You could have a really big lens, but most modern telescopes don't work with lenses, they work with mirrors. And how do you do that? How do you have a lens or mirror, excuse me, that is many feet across? That's a big mirror, and but still made so carefully that there's no bumps in it, that curvature is exact. And then furthermore, how are you able to transport it? How are you able to actually have the telescope turn? Because unless your telescope is designed to just look at the same point in the sky all year round, you need to have that telescope on some sort of, system of movable parts. It needs to redirect where it looks throughout the sky. That's true of just about every telescope. Yeah, they have to be able to rotate and twist and turn. So how do you have such a big mirror that can still do that? And then when we are looking at things from the surface of Earth, we're looking through Earth's atmosphere, and that creates blurring. Okay. So this actually is something we'll come back to. So this idea of having blurring is super important because there are certain things we just can't see when we look through Earth's atmosphere, and everything is affected by it to some extent. And some atmospheric conditions are worse than others in terms of creating a blurred image. All right. And this is just kind of summarizing the same aspects with a picture actually in each case. So we got this is and specifically this is showing the atmospheric effects. So we have turbulent layers in the atmosphere, and that creates kind of a scattering of the light. Quick key concept here, key term, active or adaptive optics. So this is how we can use computers to improve where we point the telescope and how we connect telescopes together, how we can compile images, multiple images into a single one. So this term, adaptive optics, really just refers to computer-aided telescopes. Okay, so it matters in terms of the production, so the actual engineering and manufacturing of telescopes, being able to make them bigger, higher quality, has crucially improved due to computer design. Having the actual gears and directing of the telescopes be computer controlled rather than controlled by humans, because of course if you go back 100 years you would see people cranking gears, moving them by hand, taking careful measurement, sure, but doing everything by hand. And then of course originally it would have been motorized, with large sort of gas powered motors, and then electric motors, but still you know rougher gear systems, and all of that has just been made much higher quality and with much smaller controls, finer controls, you could say. And then taking account of atmospheric conditions. So you can actually have a mirror now that can change its curvature to account for different atmospheric conditions. So you can have a mirror that's composed of individual mirrors that can sort of shift and deform, and you can account for that. Some of these kind of downsides or aberrations of telescopes. Right. So now we're going to run through telescopes. It's just kind of a fun historical timeline with some key points shown over a few slides. So we're going to cover modern astronomical telescopes going back to 1948. So you could think of this decade, the 1940s, as being the first of modern telescopes. Although they've changed a lot, this is, if you kind of make that division, um, this is where we started seeing telescopes that could do things comparable to what they can today. Examples include the Hale telescope, which was placed on Mount Palomar here in California. It had a 200-inch mirror, so it was a reflecting telescope completed in 1948, and that size is equivalent to 5.1 meters. Right here, you can see the large reflecting telescope, the Hale telescope. All right. Then moving forward, you've got the Very Large Telescope, completed many years later. Obviously, we jumped forward in time quite a bit to sort of show another key moment. Completed in the year 2000. We have a set of telescopes, four of them operating together, and each one is 8.2 meters. They're also reflecting. Notice they're bigger, right, by a few meters. Four of them working together can, you know, either look at four separate things or look at the same thing at slightly different angles and compile those images. Here we have a binocular telescope, so kind of a innovative design, like a pair of binoculars you would hold, right? But instead, this is just a really large telescope version of it, completed in 2004, and had a pair of 8.4 meter mirrors. These two incredibly large mirrors were not designed to look at two separate objects, unlike potentially the set of four that I mentioned before. They're used together to look at a single object, but by having two telescopes working together, be able to improve the optics. Now on to 2007, the Gran Telescopio Canaries, so built in the Canary Islands. And that idea of building telescopes on islands is not unusual because of the smaller amount of light pollution. No, big nearby cities lighting up the atmosphere, because essentially cities send a lot of light up that reflects off certain layers of the atmosphere and sort of makes the atmosphere glow. Maybe you've noticed this when you can sort of see cities glowing in the distance, even when you can't see the city itself, and you see it glowing in the sky. Well, putting a telescope on an island can get around that, although many islands are not ideal because they might be flat and very humid, right? So you'd have way too much moisture in the air to get good, conditions for viewing the sky. Some mountains, however, are drier and have mountains, and or at least one or the other. And so, some mountains in Hawaii are well suited to that because you want to go up to that higher elevation, both to get away from coastal moisture and things like fog, but also to get a little bit higher up, so you're looking through less atmosphere. So, that's the case with this telescope on the Canary Islands. And the number here is one 10.4 meter mirror. So we're getting bigger and bigger mirrors. And so you can see that, just in the last couple of decades, people have gotten better at building larger mirrors. Okay. And then we get up to the biggest one of them all, with a great name, I think, the European Extremely Large Telescope. And I was meaning to check because I have read about it, but it's easy to get these things mixed up. I'm 90% sure this is being built in South America. The European Space Agency works closely with South America in terms of a lot of their launches and observations. And I think this is being built in the Andes Mountains in Chile. So, really high location, very dry, and otherwise inaccessible, but the whole town has been built up in order to complete this project. And it's really pushing the size with a 3.93 meter mirror. So it's by far going to be the largest mirror um, telescope in existence. And I don't think it's actually going to be finished this year, like so many large, you know, projects that cost tens or hundreds of millions of dollars. They tend to get delayed. All right, so we'll take a break in just a minute. Um, but before we do so, I just want to introduce this concept because it'll be a nice segue to what we'll talk about afterwards. And that's transmission through Earth's atmosphere. Okay. So this slide right here is both a reference to something we saw before, namely the content in chapter 5 and the whole discussion about the electromagnetic spectrum. And that would be everything from gamma rays to radio waves. So literally the spectrum is represented across the horizontal of this figure. And this idea is also going to be really well suited to what we're about to see in terms of talking about telescopes that don't look at visible light. Because so far, that's all we've been talking about. We've been talking about telescopes that, yes, are modern in the sense of having very large mirrors and are modern in the sense of, being all about this, light gathering power and resolution power instead of magnifying power. Well, great. But then what about other types of light? I told you we talked about it, but we haven't yet, right? We haven't actually talked about a radio telescope or a X-ray telescope. So let's set the stage for that discussion. So to think about why we would have other types of telescopes and why we might not see them on the surface of Earth, let's take a look at the whole spectrum, again from gamma to radio, and which of these different types of electromagnetic radiation are actually able to make it to the surface of Earth. Well, a quick survey of the figure shows us that really just visible light, a little bit of infrared, and a significant range or band of radio waves are able to make it to Earth's surface. All other types of electromagnetic radiation, which includes all of the gamma rays, all the X rays, most of the ultraviolet, although not all of it, some ultraviolet does make it to the surface, which I failed to mention, right? Which is why we can get sunburned. And a good chunk of the longer wavelength infrared and the microwaves, which would be right in between infrared and radio, although not labeled in the figure, all those types of light do not make it to the surface of Earth. So again, most infrared, microwaves, most ultraviolet, all X-rays, and all gamma rays don't make it to the surface of Earth. So, when we talk about visible light and our ability to see it, not only was it the light that is being, produced by the sun, but it's also the light that is able to pierce the atmosphere. Now, some of that has to do with, its greater intensity, because since it is the peak output of the sun, there's more of it. So that's part of the reason it's able to pierce the atmosphere. But the atmosphere is also inherently transparent to this range. Okay. And that not saying that, the atmosphere is, designed to be transparent to the light. It just matches the particular gases that we have, that the atmosphere is composed of. And it's sort of because of the size range of the light and the size range of typical atoms, molecules, and that the agreement between the two. The- to quickly say why all these types of light don't make it to the surface, it's sufficient to just say that they scatter. That there's a lot of reasons why they're doing that, but think of it as that they end up just bouncing around and and in doing so bouncing in random directions and therefore never making it to the surface. The, so you have a collision of the light with the gases that compose the atmosphere, and that collision causes them to just bounce away after many successive collisions. Right, so it's like trying to shoot a BB through like a big array of like bars and pins, and you're never going to be able to do it. It'll just ricochet off and bounce away, and never make it through. And so the atmosphere ends up acting as a impassable, you know just network of things to bump into for most types of light. That is absolutely what you should expect for all of the high energy, high frequency, short wavelength light. So gamma, X-ray, and ultraviolet, it there's no reason any type of light like that should make it through any atmosphere, because or it really, any gas, let alone a liquid, because short wavelength light is more likely to collide with molecules, because you get to a point where the light is shorter than the size of the molecule. You've got a molecule that's, a 10, 10 to the negative, 8 across, right? So you've got this molecule that has a size of 10 to the negative 8 meters, just a number that's realistic that I'm just throwing out. Okay. Just think your scientific notation, 10 to the negative 8. You've got a light wave with a wavelength that's like 10 to the negative 14 in the case of, like X-rays, or, gamma rays. Gamma rays maybe 10 to the negative 12, and also up to 10 to the negative 10. But the point is that all those are smaller numbers, okay? 10 to the negative 12, 10 to the negative 10. That's a really small number, right? A lot of zeros. 10 to the negative 8, not as many zeros behind the decimal place. So if something smaller, interacts with something bigger, it just smashes into it and it can't get around it. So that's why all the really short wavelength light cannot pass through gases. So they just get scattered away. They actually turn it into heat. So a lot of energy is transmitted to the atmosphere because of the incoming gamma rays, X rays, and the shorter ultraviolet, right? With the infrared, the reason the reason that's not getting through the atmosphere is kind of because of special conditions. It's able to make the atmosphere vibrate in particular ways. So the energy just happens to be absorbed, kind of in the same way that a microwave can cook water because of what I described as resonance. So, for whatever reason, all this light is getting scattered away. You have no chance of observing it, no matter how good your telescope. So, astronomers and scientists that want to observe these other forms of electromagnetic radiation have to do it above Earth's atmosphere, or at least you say outside of, which is above, right? So that's going to be done. We don't have any telescopes of any kind based on, say, the surface of the moon or something, but that would be one way to do it. Instead, we put our telescopes in space. Almost exclusively, we put them in orbit around Earth, along with all our communication satellites and all the other satellites that are up there. So we put satellites, or we make telescopes into satellites. And that's how we achieve the viewing of these other types of electromagnetic radiation. And that's the names. The names here correspond to well-known satellites that observe that type of EM, electromagnetic radiation. You can see some of the names for gamma ray observation, X-ray, and then also the long radio wave, and even the James Webb Space Telescope right smack in the infrared range. The Hubble was actually observing stuff that we could have seen on the surface of Earth, but that we could see better in space because of an improved clarity. Okay. So even the stuff we can see, we're probably going to see it better in space. I haven't mentioned radio much other than I said that it got it through. Okay. It gets through because radio waves are so long, they don't even notice the atmosphere. It's like, you can walk through, a cloud of dust and it doesn't slow you down, right? Because you're so much bigger than each particle of dust. Same thing with a radio wave and the gas that makes up an atmosphere. The very long wavelength, many meters, means that radio waves can just pass right through an atmosphere without, even noticing it, so to speak. Many radio waves can pass through a whole planet, right? They can pass through solid material with hardly slowing them down, right? Or redirecting them, scattering them. So that's why we should expect radio waves to make it through easily. And there's going to be no space-based radio telescopes because, well, as we'll see, turns out they're actually they're really easy to see on the surface, and there's a good way to do it. Okay, so that's a rundown of all the different types of electromagnetic radiation, and we'll segue into that. But let's take a 5-minute break before we do so. Let me pause. Okay, so continuing with chapter 6 on telescopes. All right, there we go. So I had mentioned that we would be talking about radio telescopes, and let's do that. Okay, so radio telescopes. Well, like visible light, radio waves can penetrate the atmosphere. We saw that, right? Well, the two main types, visible and radio. All right. So looking at, and that means we can have observations on the ground. We can have a ground-based radio telescope. When we look at radio waves, we're able to see a all new view of the universe. So this might kind of sound like a trite thing to say, like, oh, it's like, oh, you get a whole new way of looking at things. But it really cannot be overstated that radio waves are incredibly useful for answering all types of questions. All right. Recall that radio waves are produced by both very cold objects due to thermal radiation and very energetic objects like black holes because of accelerating electrons that act like antenna. So you've got some, wide variety of sources of radio waves. It's important to point out that radio waves are not sound waves. We definitely kind of think of the two as the same because we think of a radio as being something that we listen to. But of course, that's because the radio, like in a car, is picking up a radio wave and then translating that with a circuit into a signal that's sent to a speaker, and the speaker vibrates, and we just hear that the vibration that's created by the speaker. But that requires that process of just turning one signal into another. And but the vibration from the speaker is not itself a radio wave. Instead, it's the transmission. And in fact, as we spoke about, radio waves are also what our cell phones use. So it's sure, radio is FM, AM, but it's also cell, right? Bluetooth is even a form of a radio wave. So early radio astronomy started back in the 1930s, kind of by accident. A man called Carl Jansky was one of the first to build a radio telescope. And it started because of studying radio communications, which were a new and emerging field at this time. So, kind of between the world wars, a lot of countries started to investigate radio communication. It was not widely used in World War One, for example. There's kind of those being some milestones in history, some key reference points. But of course, by World War Two, radio communication had become very common, as had radar. But neither of them was used, back in the 1920s. All right, so we then found, or Yansky found radio waves from an unknown source, so not coming from a different military or a different country, but instead kind of coming from all directions and maybe coming from space. These waves appeared 4 minutes earlier each day, which then I don't know if Yansky himself or someone else pointed out that meant that they had to be coming from deep space because that meant that each day, because they were always coming from the same direction, but the solar day changes relative to the sidereal day by 4-minute increments. That means that according to a clock that's based off the solar day, the waves would come at a different time. So if you ever see something that comes at 4 minutes different each day, then you know that signal is coming from deep space, just outside the solar system, right? So in other words, not from the moon, not from the sun, right? And what those waves ended up representing, these radio waves making their way to Earth, was that they were coming from, or a source. The source of them was the galactic center, so the center of the Milky Way galaxy, the galaxy of which our star is part of. And we now know to hint at something that we will see in future chapters, that this source has to do with the the energy involved with galactic centers in general, and with a phenomenon known as supermassive black holes. So, what can we see of radio astronomy? All right. So, well, here we're looking at a nebula in different wavelengths. This is kind of a cool aside that extends beyond radio astronomy. Notice that this these are all images, right? But yet only one of them is visible light. So this is showing the Crab Nebula in all these different sections of the spectrum, and kind of in the order that we're not used to, in that radio is all the way on the left. We're kind of used to reading from, short wavelength to long wavelength. This figures the other way around. So, but looking at long wavelength all the way down to very short wavelength gamma rays, all for this same nebula, well, it looks different in each different band of the electromagnetic spectrum. So because what we're seeing is different things. We're seeing in some cases, a particular molecular, process because of some sort of stimulated emission because of incoming light. In other cases, we're seeing some thermal radiation. In yet other cases, we're seeing accelerating electrons and the emission from them. And so all different signals in different cases. And when you see images like this, you might be now with the knowledge you've learned in this class, realizing that, wait, if I can't see ultraviolet, why is ultraviolet represented as white? And if I can't see X-rays, why are they blue in this figure? Well, that's just a color that has been assigned to them. These are not what they look like. Obviously, they are invisible waves. Radio waves don't look like red, yellow, and blue. Instead, we just assign colors to particular wavelengths. Sometimes in a scientific journal, there'd be some sort of like bar to tell you exactly what the colors correspond to, like a legend. But usually in a textbook or just like, popular publications, you wouldn't see that. And you just got to remember these are just artificially chosen colors. Okay. But to go back to something that I already said, but here it is in writing, what can we study with radio waves? In general, very cool objects like molecular clouds, where the thermal radiation is all the way in the radio. Okay, remember that our sun, its thermal radiation is in the visible. So having a thermal radiation spectrum, a continuous spectrum in the radio means really cold. And then really energetic objects, where the electrons are accelerated to great speed and act like giant light year long antenna. Okay, so thinking about the advantages and disadvantages of radio waves. So we're still talking about radio waves. The advantages are that we can see them all day and all night. The sun doesn't get in the way. Okay. Weather doesn't matter. We don't have to worry about atmospheric conditions like we would for visible light. And, unlike visible light where the sun washes everything out during the day, radio waves pass right, through that sunlight. As we already said, we can view things that we wouldn't be able to see, okay, with any other particular band of the spectrum. Radio waves can penetrate dust in our galaxy. So not only are they reaching the surface of Earth because they can penetrate atmospheres, and good thing they're harmless. Going back to what we were talking about before, because being so long and low energy, they don't cause harm. But they also allow us to look at parts of the galaxy or other galaxies that would be totally invisible to shorter wavelengths. So we can't look towards the center of the galaxy in the visible spectrum because it's just totally obscured. It just looks black because there's so much dust between us and the center of the galaxy. But radio waves can pass right through that dust. So they act like X-rays do for soft flesh, right? So X-rays pass through soft flesh and they bounce off, like harder material, right? Well, radio waves, they pass through gases, even fairly high density gases, and then what we're seeing is the source of them. So we're not seeing them bounce off of things because there's no way we could. We'd have to wait thousands of years, right? If we actually wanted to send a radio wave and see its reflection, which is how X-ray images work. So it's sort of like because of the different principles, we're using these two types of light very differently. But we're seeing the source of the radio wave from behind the thing that would obscure shorter wavelength light. Hopefully that made sense. And it allows us to see cool hydrogen gas, which is really important because hydrogen is the primary building block of the universe. It's the most common element out there. And it turns out that a lot of times it has signals that are in the radio range. There's just really important key signals that allow us to map things really effectively, that correspond to radio. Disadvantages is because of the really long wavelength. We're not going to see anything small with radio waves. It's never going to help us probably discover exoplanets because the scales is too small. Um, the the telescopes that observe them need to be very large, right? So the actual the observation, because if you have a really long wave, your mirror has to be appropriately bigger as well, right? Because you're trying to focus a much longer wave. Well, you have to have, you know, a mirror that can capture, the whole wave at least. And then since we use radio waves so much for communication, we have to think about, are we interfering with the signals, and how do we avoid that? Luckily with computers we can probably filter out most of it pretty effectively these days, but it's just something that you have to at least design around, because you don't want to have a false signal, think you're getting a radio wave from space when it's actually just coming from some sort of communication. Okay, so a typical, and I meant to point this out before, but this, like right here, right back here, that this, by the way, is a radio telescope. You probably already know, but just to make it absolutely clear that this thing that you think of as, a maybe a satellite dish, right, is a radio telescope. At least that's one use of things that look like this. Yes, they can be used to, pick up communication signals. So in that case, we call them a satellite dish or communication dish, but they also can be used to pick up incoming signals, so to speak, right? Invisible light from space, radio wave electromagnetic radiation. Lots of names for the same thing. So when we look at this is what we call a big array of radio telescopes. And so the reason this is a telescope is because the whole dish is the mirror, right? It's not shiny like a mirror that reflects visible light, because it doesn't need to be. Because the longer wavelength, it doesn't have to have that surface be so smooth. The surface need not be smooth. It just needs to be smooth enough. In this case, not very at all, right? Because the wavelength is so long. But you do need big size, okay? And sometimes the size is such a constraint that we can't build a big enough radio telescope to really capture some of the waves we're interested in, or just be able to take advantage of that same principle of being able to focus more of them and see things that are fainter. Because if we can get a bigger and bigger radio dish, then we can increase our light, absorbing power, what we called the drawing a blank on the name they used. Sorry for the rapid slides here. Light gathering power. Yes. So our light gathering power, as well as our resolving power, are going to be improved by having a bigger dish. Okay. But instead of having one really big dish, okay, we can increase the resolution, right, which is proportional to the area, or increase the radio wave gathering power proportional to the area squared by having many dishes working together. Okay, so we observe some point, some object, some observational goal with many telescopes, so multiple telescopes, and we combine their signal. This type of combining multiple radio telescopes to operate as one single large telescope is called interferometry. Essentially, it's almost like this whole array is acting like one giant dish. It requires, good quality communication between them, so there's no delay in the signal. Well, there's always going to be some delay, and if that delay is needed to be accounted for, then it can, based on the travel speed of the signal. But usually, some high quality fiber optics connect all the dishes with one central processing point, where all that data is getting compiled, and so that the whole array can act like a single dish. Right. So what we're doing here is we're increasing the effective size of the telescope, okay, by having all of them act together. This means that we can really build pretty impressive radio telescopes, because this idea cannot be as applied with modern technology in the same way to visible light telescopes. Although we do combine visible light telescopes, we can't do it in this, really say, oh, hey, let's just put a bunch of visible light telescopes in a big array and it's just going to act as one mirror that's literally a mile across, right? It because remember like the mirror has to be bumped like perfectly smooth. So we can't just say that we're simulating a perfectly smooth mirror by having, a couple of mirrors that are, 500 feet, 500 meters or 500 feet away from each other. It's, there'd be too much loss of data. But with the case of the dishes, we really can, especially for longer wavelength. So we actually are operating like this, like a single giant mirror, but for radio waves. Would it be possible in the future maybe to do that with visible light? Maybe, but it really is an attainable thing currently with radio telescopes, and it's allowed for some pretty impressive scaling because it means that you can really just continue to scale up the size of an array of radio telescopes to the point that arrays of telescopes are being built and already have been built that are many kilometers across. And discussion of building ones that span entire sections of continents. So you can have a radio telescope that is hundreds of kilometers across, which quite possibly will exist, within your lifetime. So, really there's a, a noticeable, achievable kind of progress with radio telescopes, which makes it an interesting field in terms of its current advancement. There are cases where single big dishes have been built because usually because of the particular radio waves that those dishes were studying. Because when you get to the shorter end of the radio spectrum, your interferometry starts to become less effective. If you're interested in microwaves, for example, because then you're losing too much data by having those big gaps between the dishes. So then you might want one big dish. Some, ones that have been built are the 100-meter Green Bank telescope, right? So 100-meter size, way bigger than the biggest visible light mirror. Okay, completed in 2001. Although it's pretty impressive how big that visible light mirror of the extremely large one is, considering it was, some about a third the size. Okay, and it's the largest fully steerable radio telescope. So it can actually change where it points. It's not just pointing in one fixed direction. The biggest radio telescope was, because it no longer exists, the 300-meter, so triple the size of the one we just talked about, Arecibo telescope built into a natural valley indentation in the tropics of um, Puerto Rico, so kind of in the hills or mountains of Puerto Rico. And it was in operation until 2016 when a failure of the cables during a closure and some plans of eventual repair. Um, the repair never happened, and the cable snapped, and this whole section here, which is the focus and basically where the data is being collected, fell into the dish, damaging it to the point that a repair was completely out of the question, and the whole thing had to be completely just scrapped. There's no plan to rebuild it, um, but there are, some other large radio dishes being made, such as FAST in China at 500 meters, although I don't know if it's complete. So now the quick rundown through the James Webb Space Telescope. Okay, so I'll talk a bit about the history of it, and then I do want to get to where it's located. Okay, so let's quickly check out that this is a telescope that was pretty recently launched. So I'd say first draw your attention to the bottom of the list here. A lot of things going on here, but 2021 was when this space telescope was actually launched. So it's only been in space for a few years. So we're really near the beginning of its you know lifespan, the beginning of its career as a telescope. Okay. This points out that it was planned for 2007, but it wasn't launched till 2021. That's the type of delay that I mentioned. But it's actually impressive that it even made it through. There's points where the project nearly got completely just canned and trashed, but it did not. And it's been a major success. There was no issues about the launch, no damaged machinery or optics. It is completely operational in the best possible way. Um, it has a kind of minimum planned operational life of 5 years. It's very unlikely that it will only last for 5 years. It will most likely last for much longer than that. 20 years is a reasonable estimate. Um, to put that in perspective, Hubble was only planned to operate for 15 years, but it's been running for 50 now, and it's still absolutely, possible to be used. Um, why are these numbers so disconnected? Maybe just because the programs want to lower expectations and don't want to promise more than they can deliver, so they kind of go with a worst case scenario, just so that everything can be based off of that. Which is sort of what I'm saying is that if 5 years it does happen, well then they know that in those 5 years they have certain observational goals and they want to focus on those and get those key things done that they had planned. And of course those plans get adjusted as new discoveries are made and new fields become a focus of astronomy. But the point being is that there are things that they want to get done that are high priority, and you want to do those in the years that you're confident in this case space-based telescope is going to work. There's some naming controversy because of the individual it's named after, which is totally understandable. Um, my 2 cents, I don't think it should have been named after an administrator in the first place, rather than a scientist. All right. So now, what type of light does it look at? Well, it's actually meant, and I know there's some concept questions, so I'm going to skip over them, or involved questions. It the James Webb Space Telescope, the JWST, primarily is an infrared telescope. It does look at a little bit of the red, yellow, and orange end of the visible spectrum, but is primarily a radio telescope. Sorry, an infrared, wrong word came out. An infrared telescope. Why is that? Why focus on infrared? Seems like, if you're going to build the best telescope, why not make it visible? Well, there's some really good reasons. Um, One is to do with deep space. So when you look at the spectrum that the James Webb Space Telescope is, going to operate best in, okay, and it actually kind of looks like a visible light telescope in terms of having a mirror, and that's because we're talking about infrared here, not radio waves. So there's like these smooth mirror segments that are used to focus the infrared, because the optics of infrared are going to work very similar to the optics of visible light because they're so similar in wavelength. But again, getting back to infrared, it has to do with the redshift. So the redshift is a topic that's covered in chapter 5. If you haven't seen it, go back and review it. It's something that you want to know. And what happens is, as things get older, as we look further back in the history of the universe, closer to the Big Bang, we look at objects that are moving away from us faster. This is just fundamentally true. We'll talk about why when we get into cosmology. But suffice to say that the further away a galaxy or some, you know, cloud of stars, or maybe a dwarf galaxy, just all these things that, exist on a bigger scale than stars. Whatever that cosmological object is, when it's further away from us as an observer in the Milky Way galaxy, it is moving away from us faster. The best, simplest way to understand it is just to remember the universe is expanding, and as things expand, and the whole universe is growing, well, any 2 points are always moving away from each other. And the greater distance between those 2 points, the greater the relative motion. And there's a great analogy that's made between the growth of the universe from the Big Bang to today and a loaf of bread with air bubbles in it, which seems like a weird comparison, but it actually describes this idea, which isn't that intuitive. A lot of people kind of say, well, that can't be right. Why would something further away be moving away faster? But it really is, and it's just a fact. Applies to bread just as much as it applies to the universe. So we'll get there. We'll talk about the expansion of the universe, not for a while in terms of the chapter content, but it's touched on a tiny bit in chapter 1, and you can look ahead. But we did talk about the redshift in chapter 5, or it is covered in chapter 5. So now, just to summarize, further objects, by further I mean 13 billion years, or 13 billion light years away, or 12 billion light years away, well, those very distant objects will have a very great redshift because of their very large relative speed away from us. Blue shift is when something's moving towards you. But all these galaxies are moving away from us. We're also moving away from them. Okay, we're not the center. So everything's redshifted when you get far away. And well, notice that I just mentioned distances, but all the labels here are times. Well, that's because of that relationship between a light year and, a year. If I look at an object that's 12.6 billion light years away, because remember, light years a distance, the distance that light travels in a year, I'm looking at an object that's also 12.6 billion years old. Every distance corresponds to an age in astronomy, every time. So when we look at those really distant objects, we're also looking at very old objects, which means they're very primordial. By primordial, I mean they existed shortly after the Big Bang. So the James Webb Space Telescope primarily was designed, with a wonderful goal in mind, and that is to further understand the beginning of the universe. And it's really well suited to do that, to explore aspects of the very early cosmos shortly after the Big Bang in ways that we just could not do with other telescopes, not with any of our, radio telescopes, not with any of our space-based telescopes in any part of the spectrum. So really, really pushing the envelope on questions about the universe. Okay? Brief history of time. I love this, but we will cover all these key moments in the Big Bang, and shortly thereafter in the whole chapter, which is really really a neat idea. Kind of all these things that happened as the universe was formed based on our current understanding. All right, so the kind of the time frame, which I will mention, is that the James Webb Space Telescope can potentially study and is starting to, data is coming in and being analyzed and publications are, coming out, but kind of the consensus hasn't been reached, so to speak. But is that the era of the first stars can be investigated, which corresponds to 200 million years after the Big Bang. So we're talking really, really early universe. This is a time frame that has never really been studied before. So, that our galaxy wasn't even formed until 1.2 billion years after the Big Bang. So this is looking back to a point where before the Milky Way even existed. Okay. All right. So then that's kind of a cool goal of the telescope. This is a kind of a summary of all the different parts of the spectrum. Here's the mirrors I mentioned, right? So it looks similar to a visible light telescope, but you can kind of tell, that because of these the look of them, you would never see sort of these colored lenses for a visible light telescope. That does have to do with its infrared focus. Right. It's talking about the instruments, this because it's not just one telescope. It's an array of different things that are all kind of built together, and they have different names, different teams worked on them. So keep neat summary there. This is showing those teams. Okay, now the thing I wanted to mention is where is it? Because this is the other thing that is truly interesting about it and relates nicely to a lot of the stuff we're talking about orbits and so on. Okay, so the James Webb Space Telescope, the JWST, is not in orbit around Earth. Let me just say that, which is unlike Hubble and unlike all those other telescopes that were shown in the figure when we talked about the spectrum and the atmosphere. So it is not a satellite. So what is it then? Well, Earth orbits Sun in an ellipse, okay? And because of that elliptical orbit, and because of the different gravitational pulls, there are these special points called Lagrange points, which are not explained in Kepler, Kepler gravity, Kepler orbits. This is an idea that is an extension of Kepler's laws. So not covered in Kepler's three laws, but if you kind of take another step and do some math with Newtonian mechanics, so understanding the universal law of gravity, understanding those laws of motion, you can come up with this idea that there's these special points called Lagrange points where the forces of gravity balance. And there's five of them for every elliptical orbit. In this case, Earth's elliptical orbit around the sun. You might be like, wait, why is he talking about Lagrange points? You'll see. There's always one between the Earth and the sun, and this would be the chain between any planet and the sun, but I'll just say Earth and sun from now on. So there's one point between Earth and the sun, one of these gravitational balance points. There's one beyond Earth. There's one on the far side of the sun, and there's two at these key points around the elliptical orbit. All right. And when you place an object at one of these Lagrange points, that object, like a satellite or a space-based telescope, say the connection, it stays there. And by what I mean by stays there is it moves with Earth. So look at this kind of animation here. Notice how the five Lagrange points, they don't orbit separate of Earth. And that's important because everything else does, right? The moon orbits us, right? Our own moon does. But if I was to look at the orbit of Mars, I would see Mars orbiting according to Kepler's third law with a period that is not the same as Earth's period. So the Earth would move faster and occasionally lap Mars because Mars would lag behind. So if it wasn't for the balancing of forces, L2, since it's further from the sun than Earth, would orbit more slowly and it would fall behind Earth over time. But it doesn't. Instead, it's like a fixed point, and you can place something there and it will stay there relative to Earth in Earth's orbit around the sun. Okay? And that's where the James Webb Space Telescope was placed, which is significantly further from Earth than the moon. And it's about like six times further than the moon is, which is a pretty long distance. That's no trivial mission to send something that far out. So way past the moon is this location where if you place something there, it just sort of sits there, balanced by the gravitational pull of Earth and the sun combined. And then it just faces out towards space. Far away, so we got to, communicate with it carefully. It's no easy task. But the advantage is huge because it can always face outwards. Unlike something that orbits Earth and sometimes, will be facing the sun, the telescope, the JWST can just face out towards space, away from the sun, and even away from the reflected light coming off of Earth. You can see how it makes for the ideal dark environment for a telescope. All right. So that's the just really impressive, but also hopefully fascinating aspect of this telescope, that it was placed at this point. This is a unprecedented, achievement. People have talked about placing objects at the Lagrange points for the last 100 years. They're discovered in the 19th century, but since the early 20th century, it's always been talked about, we should put things at the Lagrange points, space stations, whatever, But this is the first time something large has ever been placed at one, an operational object. So it's just an impressive achievement. I was just talking about like things that can be placed there, right? So like observing solar weather. I guess okay, to be fair, we have placed things to observe solar weather at L1. But there are some natural asteroids at L4 and L5, right? But people have thought about placing things there. You could have a counter Earth at L3, research facilities, all kinds of stuff. So maybe in the future we'll start using more Lagrange points. All right, well, that's time. Let me stop this.